In the summer of 1925, Werner Heisenberg developed the first consistent theory of quantum mechanics. The paper he wrote is cryptic, even for experts, but inside we find 4 groundbreaking ideas that rewrote the rules of physics. In this video, I will walk you through these ideas, concepts, and calculations to show you exactly how Heisenberg created quantum mechanics. Quantum mechanics was created by Werner Heisenberg in 1925 with the publication of this paper. The content is hard to follow, some sections lack continuity, and some mathematical steps look like magic. The goal of this video is to change that, and only with the help of not very advanced physics and plenty of mathematical manipulation, I hope to make Heisenberg's paper more accessible. By the end of this video, we will discover how the famous zero-point energy appears in Heisenberg's theory and an early draft of what later became the uncertainty principle. In this step-by-step guide, I will show you all the details so you can also enjoy the beauty of this groundbreaking paper. This video is divided into 3 parts. I will begin by showing you the experimental fact that led to matrices. Then I will introduce the 4 core ideas and calculations in the paper, and finally I will present one of the examples that Heisenberg provided at the end of his paper, including all the gory details that I hope can give you a glimpse on the work of theoretical physics. As you probably know, Heisenberg's theory of quantum mechanics became known as matrix mechanics because of the use of these mathematical arrays of numbers. I want to begin by answering one simple question. Why are matrices needed in quantum mechanics? The answer is a simple experimental observation made by the Swiss physicist Walter Ritz in the summer of 1908. This table shows some of the lines of the hydrogen spectrum. Let's take these 2 and add their inverse. And now let's look at the inverse of this line. Let's try with these lines. Now these 3. There is clearly a pattern here. One last time. I will now show you why this happens. This is the formula that Rydberg found in 1888 for the wavelength of hydrogen spectral lines in terms of 2 integer numbers j and k. R is just a constant. Multiplying all this by the speed of light, we get frequencies instead. Notice what happens when we add 2 frequencies in which the second index of one is identical to the first index of the other. Using the formula above, we find that the middle indices cancel out, and we get a new frequency with the first index of one and the second index of the other. This relation is a general result for spectral lines, and this is exactly what I show you in the examples. If I include the indices, you can see that in all cases the general formula works. This relation is an example of the so-called Ritz combination principle, and it tells us how the frequencies of spectral lines are combined to form new frequencies. This observation is the key to unlocking the ideas in Heisenberg's paper, and, as I will show you shortly, this experimental fact is the reason for the need of matrices. Since 1900, quantum physics was a collection of arbitrary and unjustified rules that became known as old quantum theory. Heisenberg changed all that after an isolation retreat in a remote island in June 1925. After his return, he wrote a cryptic paper titled On the Quantum Theoretical Reinterpretation of Kinematical and Mechanical Relationships, in which he laid out 4 rules for calculating the outcome of experiments. Everything began with Einstein's quantum theory of radiation from 1917. After completing his monumental work on general relativity, Einstein returned to the study of radiation, introducing 2 key innovations: a new process called stimulated emission and transition probabilities for describing the absorption and emission of light. Unfortunately, there was no way to determine these probabilities. The breakthrough came in early 1921 when Rudolf Ladenburg found a way to connect Einstein's quantum probabilities with classical quantities that could be measured in dispersion experiments. Inspired by Ladenburg, this idea was extended by Hendrik Kramers, who found a quantum theory of dispersion. Kramers and Max Born also discovered a mathematical relation between classical and quantum relations that was crucial for Heisenberg. Let's now dive into Heisenberg's famous paper. The key word is reinterpretation. Historians of science refer to this work as the Umdeutung paper. What everyone was searching for during the 1920s was a way to derive quantum equations to replace the equations of classical mechanics. Heisenberg built on the ideas of Einstein, Ladenburg, Kramers, Bohr, and Born to find the quantum equivalent of physical quantities from a classical theory. He starts by setting one of the core ideas in which his quantum mechanics is built. It is advisable to completely discard unobserved quantities, such as the electron's position and period. Instead, it seems more reasonable to try to establish a theory of quantum mechanics in which only relationships among observable quantities occur. This is one of the most radical ideas in the history of physics, one that leads to debates even today. Heisenberg proposes here that quantum mechanics is only a theory about experimental observables. In his paper, these are the transition amplitudes and frequencies. Although this idea is usually attributed to Heisenberg, one of its main proponents was Wolfgang Pauli. His letters show that by the summer of 1925, he had convinced most of the key figures of quantum theory about this idea. This is something that Einstein and Schrödinger strongly opposed. For them, physics is about describing nature as a whole, including all its underlying mechanisms, even those that we cannot measure. We could say that, with this sentence, Heisenberg began the infamous shut up and calculate approach. Let me know in the comments if you have an opinion about this idea. After this, Heisenberg begins his ramblings. I stop following the paper here and present the ideas in a more coherent order, pointing out to the corresponding results in the paper. The first concept is position. The classical view of the electron orbiting the nucleus was enough for atoms with a single electron, but failed with all the others. After his work with Born, Heisenberg knew that a classical periodic motion of an electron in a stationary state n can be described as an infinite sum of oscillations. This is called a Fourier series. A more general way to write this is by using a complex exponential instead, where the sum is over all positive and negative values of the index alpha. I will later drop the summation range to simplify notation. The factors A alpha are called Fourier modes, and Kramers showed in his doctoral thesis that these factors are directly related to the transition probabilities between states introduced by Einstein in his paper on quantum radiation. The position is a real quantity. Forcing all this sum to be equal to its own complex conjugate implies a relation between the negative and positive Fourier modes. This relation will be very useful later. Here Heisenberg introduces his first seminal idea. According to the correspondence principle, the classical frequency of the orbital motion of the electron and its harmonics get replaced by the transition frequencies between atomic states. Alpha omega becomes omega nk, where n is the current state of the electron and k is any other state that the electron can transition via a quantum jump. Just for clarity in this video, I will use the subindex k as short notation for n minus alpha. Now we can write the position of the quantum electron in this way, where the classical Fourier modes are replaced by transition amplitudes with two indices to match the transition frequencies that obey the Ritz combination principle. Just like in the classical case, forcing the position to be a real quantity implies this relationship, reversing the indices of the amplitudes is equivalent to checking its complex conjugate. This relation corresponds to Heisenberg's position reinterpretation and the word kinematics in the title of his paper. Note that the positive values of alpha represent quantum transitions between the current state n and lower levels, whereas the negative values denote higher levels. With this expression, Heisenberg built a tower of so-called virtual oscillators. The next concept is motion. I bet many of you were not expecting to find Newton's second law in the foundational paper on quantum mechanics, but this is Heisenberg's starting point. Writing the force and acceleration as functions of position, dividing by the mass of the particle and collecting terms on the left-hand side. Heisenberg renamed this ratio just F. His idea is that depending on the physical system of interest, all you have to do is to identify the potential energy, calculate F, and properly write this equation of motion in terms of the quantum position as defined in the previous section. This concept is the mechanics in the title of his paper. As examples, for the harmonic oscillator, F is just omega naught squared times x, whereas the so-called anharmonic oscillator has an extra term with x squared. In general, for any function, we can expand the function as a power series of x. And here Heisenberg realized that we need a proper definition of how to calculate powers of x, which takes us to the third concept, multiplication. This concept is probably the most important and revolutionary in the paper. Back to the classical definitions, let's see what the product of two positions x and y is in terms of Fourier modes. For this, we simply multiply two Fourier series, where A are the modes of x and B are the modes of y. Note that the exponential now combines harmonics of x and y. However, we can introduce a new index tau, which allows writing the product as a new Fourier series. Defining the new Fourier modes in terms of A and B, we explicitly find that the product of two positions x and y gives a series that has the same structure as x. This is one of the great properties of Fourier series. We can calculate the product between y and x instead. Following the same steps as before, we find that the order of the product makes no difference. We call quantities that satisfy this relation commutative objects. A common example is real numbers. The order of the factors does not affect the product. Now we repeat this, but using the quantum reinterpretation of position and frequency introduced before. Taking the product, we must be careful with the indices. And just like in the classical case, the two corresponding frequencies appear added in the exponential. But now we have a problem. Note that the two frequencies cannot be combined into a new frequency, like in the classical case, because the indices do not match the Ritz combination principle. This would mark the end of Heisenberg's efforts, because the product of two series does not produce a new series. But here comes the bold move. Heisenberg proposed that this is not how quantum objects are multiplied. He wants the two frequencies in the exponential to have the indices in such order that the Ritz combination principle can be used to convert this sum of quantum frequencies into a single new frequency. Remember that the Ritz combination principle is an experimental fact. Heisenberg simply took this feature of nature and used it to invent a new way to manipulate transition frequencies. His multiplication rule is that the second index of the first amplitude must be equal to the first index of the second amplitude. In this way, the two frequencies in the exponential can be easily added using the Ritz combination principle. Now we proceed. Just as before, we rename the product of amplitudes and find that the product of these two quantum objects is a series like the original. We can repeat the same steps to calculate y times x instead, but now we find that the indices are arranged in a way that the two products are, except in very special cases, not equal. Here Heisenberg found that a consequence of his quantum reinterpretation is that quantum objects are not commutative. This is the bold conceptual innovation that makes this paper the foundation of modern quantum mechanics. This weird multiplication rule made Heisenberg very uncomfortable. In the paper he wrote, "This multiplication rule is an almost necessary consequence of the frequency combination rules." He accepted what his theory was telling him, but could not make sense of the meaning of these non-commutative objects. After his return from Helgoland, he expressed his concern to Max Born. What are these objects that obey these rules? Let me bring back the way the transition amplitudes are combined. Heisenberg was baffled by this relation, but today even a freshman student would recognize it as matrix multiplication. Believe it or not, Heisenberg didn't know about matrices. This is how Hans Bethe, one of the great students of Sommerfeld and Heisenberg, described it.
So he said we should only talk about experimentally observable quantities, both the frequencies and these amplitudes, but should forget about the motion of electrons in orbits. Then he discussed just how these quantities Q and pKn should occur in the theory. How would you form kinetic and potential energy from them? And he found that these quantities obeyed very strange multiplication rules, which he had never seen before. But he wrote down these multiplication rules. P and Q just did not behave like ordinary algebraic quantities. When he came home to Göttingen, Max Born told him, but Heisenberg, what you have there is simply the multiplication of matrices. Now you all learn about matrices probably in your freshman year or at most in your sophomore year, but Heisenberg had never heard about matrices.
Thanks to Born, Heisenberg discovered that quantum objects follow the rules of matrix algebra, but this only happened after he wrote his paper. Before we judge Heisenberg for not knowing about matrices, the same was true for most physicists of the time. Matrix algebra was so unknown that the paper that Born and Jordan wrote following on Heisenberg's work began with a full section explaining the basics of matrices. The fourth and final concept introduced by Heisenberg was a new quantization rule. I remind you that the old quantum theory was mostly based on the rule developed by Bohr and Sommerfeld. This was very successful for describing an isolated hydrogen atom, but it failed in light of new experiments. This rule worked as follows. First, write the classical equation of motion. Then solve the equation to find the classical solution. And finally, force the classical solution to satisfy the Bohr-Sommerfeld rule. In Heisenberg's approach, the classical solution is irrelevant, because the goal is to determine the transition amplitudes and frequencies. For this reason, a new quantization rule was needed. Heisenberg took the rule from old quantum theory and replaced momentum and position by their classical Fourier expansions. Using the chain rule, the integral over position can be turned into an integral over one orbital period. We need to determine x dot squared. Since we know x, we can directly take the time derivative, and then take the product with itself. These are classical Fourier expansions, so this is the conventional product. Now we can use a trick. Since the sum over beta includes all positive and negative values, we can replace beta by minus beta in this expression, and the sum does not change. In this line, I have simply replaced every beta by minus beta. Now we can integrate over time. The orbital period is related to the frequency, so we can make this change of variables. This angular integral is not trivial, but it happens to vanish except when beta is equal to alpha. In case you are familiar with the name, this is an integral representation of the Kronecker delta. This means that when summing over beta, all terms are zero except when beta equals alpha, and this expression reduces to a single sum. There is nothing new here. This relation is just the Bohr-Sommerfeld rule for Fourier modes. Now Heisenberg tried to reinterpret this relation. The obvious thing to do is replacing the Fourier modes and harmonics frequencies by transition amplitudes and quantum frequencies, respectively. However, there is a problem. What to do with this extra index alpha? Heisenberg's reinterpretation of frequency only eliminates one of the alpha indices, meaning that a direct reinterpretation of the Bohr-Sommerfeld rule is not possible. Here is Heisenberg's workaround. He took the derivative with respect to the quantum number n on both sides. This expression looks even more complicated, but here he invoked what we could call the reinterpretation discovered independently by Born and Kramers. This relation turns classical derivatives into quantum differences. This is one of the great outcomes obtained in the spirit of the failed BKS theory that I presented in a previous video. Using this relation, Heisenberg was able to transform the quantum rule of the old quantum theory into his new language of transition amplitudes and frequencies. Heisenberg understood that this rule provides a recursive relation between amplitudes. Once you know the amplitude for one quantum transition, this relation allows finding the others. This formula and the equation of motion with the corresponding multiplication rule constitute the equations of Heisenberg's quantum theory. And these are the revolutionary ideas in the paper. Here is a summary of the key concepts in Heisenberg's paper. Position is written in terms of transition amplitudes and frequencies. These two quantities are the central unknowns of the theory because they are observable in experiments. The transition amplitudes define the intensity of the spectral lines, and the frequencies determine their wavelength. Motion is characterized by the quantum position object satisfying the classical equations. Note that Heisenberg's theory is Newtonian. This was later improved and turned into a more general Hamiltonian theory by Heisenberg in collaboration with Born and Jordan. Maybe I should make a video about that too. Quantum objects obey an unusual multiplication rule. Non-commutativity of quantum quantities is one of the central discoveries in the paper. Thanks to Born, Heisenberg and the rest of the physics community learned that transition amplitudes are described by matrix algebra, and Heisenberg's theory became known as the matrix formulation of quantum mechanics. The quantum nature of transition amplitudes and frequencies is specified by Heisenberg's reinterpretation of the old Bohr-Sommerfeld quantum rule. Here is where Planck's constant enters the equations. And that's it. This is the recipe for a self-consistent and systematic quantum mechanics. Heisenberg described it like this. Equations 11 and 16 contain a complete determination not only of frequencies and energy values, but also of quantum transition probabilities. The paper also includes two crucial questions. Probably influenced by the recent refutation of BKS theory, Heisenberg wondered about energy conservation and also whether the energy levels predicted by his theory would satisfy the well-established Bohr-Einstein relation. But the only way to answer these questions was by testing the theory with examples. This is what I will do in the next part. Heisenberg's method was a first draft for quantum mechanics. All the main ingredients are there, but he knew that a mathematical refinement was needed. He ended his paper with an invitation to such mathematical polishing of his ideas. Whether the method proposed here can be regarded as satisfactory can be decided only by more intensive mathematical investigation. The method has been very superficially employed here. In the last section of this video, I want to show you an explicit example of how to use Heisenberg's idea to a particular system. Although I will present a simplified case, I will include all the gory details because I find this a very instructive exercise. I honestly think that I understood the main ideas in Heisenberg's paper, only after going through these calculations, and I hope that they can help you too. This would let you appreciate the amount of work behind every result in the paper, and hopefully give you a glimpse of the work of a theoretical physicist. Heisenberg begins section 3 of his paper with, as a simple example, the anharmonic oscillator will now be treated. The interest in the anharmonic oscillator is that, just like the hydrogen atom, transitions between all levels are possible. However, this example requires familiarity with the methods of perturbation theory. Since I want this exercise to be valuable, even if this is your first encounter with quantum mechanics, I will only cover the particular case of lambda equals 0. This is the simple harmonic oscillator. There is a running joke that the simple harmonic oscillator is the only system that physicists know how to solve. Sidney Coleman described it better. The career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction. And if you have studied quantum mechanics and quantum field theory, you know that this is true. I will first solve this using the Bohr-Sommerfeld rule of the old quantum theory, and then using Heisenberg's quantum mechanics, so we can compare. If you watch my last video, you will like the subtle differences. As you probably know, the differential equation of the harmonic oscillator is exactly satisfied by this general solution, where A and B are constants and omega naught is the fundamental frequency of the oscillator. Comparing this solution with the general Fourier series, we immediately find that there are only two non-zero Fourier modes, and the harmonics are given by multiples of omega naught. This means that the infinite sum only has two terms. Following the recipe of old quantum theory, now that we have found the classical solution, we make it quantum by forcing it to obey the Bohr-Sommerfeld rule for Fourier modes found before, where n is an integer. Let's not forget that this sum has only two terms, one for alpha equals 1 and alpha equals minus 1. By properties of complex numbers, this reduces to a single term, from which we directly find the general expression of the only non-zero Fourier mode. Let's now calculate the energy levels of this old quantum oscillator. Note that we need to determine x dot squared and x squared. And for this we use our simple Fourier expansion. X dot is given by this, and its square leads to 3 terms. Then we do the same for x squared. The calculation is very similar. Plugging these two quantities in the expression for energy, we have 6 terms, but 2 pairs cancel each other out, while the other 2 are identical. Note that all time dependence disappears, meaning that the energy levels are constant in time. Energy is conserved. We have found the energy levels in terms of the Fourier modes. We can now replace our previous result to find that the energy levels are proportional to the quantum number n. For this reason, the energy gap between two adjacent levels is exactly h bar omega naught, and the Bohr-Einstein relation is satisfied. Here is the summary of the results. Now we repeat this, but following Heisenberg's method. Just like before, we begin with the quantum position, but instead of using the classical solution, we calculate the second time derivative to replace it into the equation of motion. Factorizing common terms, we find this relation. From now on, we will need the complete form of the indices, so I am replacing k by n minus alpha. Under the assumption that every state has its own energy, for each value of alpha in the sum, the exponent will be different. This means that each element of the sum must individually vanish. For alpha equals 0, we get this. Since the transition frequency of a state with itself is 0, we find that the same is true for the amplitude. For alpha equals 1, we get this. Inspired by the classical result, we set the amplitude between one level and the next to be non-zero, which gives us a constant value for the transition frequency. Contrary to the hydrogen atom, here the frequencies are independent of the quantum number n, which means that the energy levels are equally spaced. We can now repeat for alpha equals -1 to get this. Just like the classical case, the only non-zero transition amplitudes are between adjacent states. Using that the energy levels are equally spaced implies that for all other values of alpha, the amplitude is 0. Summarizing, from the equation of motion, we found the frequencies and the non-vanishing amplitudes. This condition, that the only allowed transitions are between states that differ by one quantum unit, is usually known as selection rules. We still need to find the value of these two amplitudes. For this, we use the other equation in Heisenberg's method, the quantum condition. As mentioned before, this equation provides a recursive way to determine the amplitudes. Since alpha can only take two values, we can expand the sum, leading to 4 terms. Using the previous result for the transition amplitudes and being extra careful with the order of the indices to get all the signs right, we find that the 4 terms reduce to 2 terms. Finally, we can write the recursive relation for the amplitudes. The next step is defining a so-called ground state. This is defined as the lowest possible state of the system. Setting this to be represented by n equals 0, we get the following. In this step, Heisenberg reasoned that transitions below the level n equals 0 do not exist by definition of ground state. Therefore, this term must be 0. And with this, we find our first transition amplitude. Next, we take n equals 1, which is given in terms of the transition that we just found. We can repeat for n equals 2 and quickly find the pattern. For any state n, this is the transition amplitude, which I will add to the summary on the top right. Note that the absolute value allows reversing the state indices without affecting the result. Also notice that we can replace n by n minus 1 to obtain this pair of relations that will be useful in a minute. The final calculation is the energy of the oscillator. Just like before, we need to determine x dot squared and x squared, but this time we must use Heisenberg's multiplication rule. For x dot, we simply take the derivative with respect to time. Here notice that all these terms correspond to the amplitude that we have to use in the multiplication rule. The product of x dot with itself gives us this long expression. Now we use that only transitions between adjacent states are allowed to expand the sum over alpha, so we get 2 terms. For the sum over beta, we have to be extra careful. Let's look at this term. From the selection rules, the indices in the amplitude can only differ by 1. Therefore, beta can only take the values 0 or 2, leading to these 2 terms. Using the same method with the second term, we find that beta can only take the values 0 and minus 2, producing the next 2 terms. Now we have to evaluate the frequencies. Since the 2 amplitudes have the same indices in reverse order, their product is just the squared magnitude. Using our previous results, the first frequency is positive and equal to omega naught, whereas the second frequency has the same indices in reverse order, so it has an extra minus. Finally, we use that the transition frequency of a state with itself is 0. Just to make sure that the method is clear, let me do the second term. Here the product of amplitudes remains as it is. The first frequency is again omega naught, whereas the second frequency is also omega naught. If this is unclear, just replace n by n minus 1 in the formula above. The exponent is no longer 0. Since we know that the energy levels are equally spaced, the frequency between levels 2 units apart is simply 2 times omega naught. Using the same procedure with the other 2 terms, we get this. Taking out the common factor omega naught squared, we have found the expression needed for the kinetic energy. The same steps are needed for x squared. We expand the sum over alpha, then sum over beta, and evaluate the frequencies. This is much easier than the previous one. And now we are ready to calculate the energy of the oscillator. Like the semi-classical case, all the time-dependent terms cancel each other out, making the energy levels constant. This answers Heisenberg's question about energy conservation. Yes, the energy of the harmonic oscillator in quantum mechanics is conserved. Now I bring back the amplitudes that we found before, because we can determine the final expression for the energy. Plugging the two relevant amplitudes, we get this. Factorizing common terms, we finally find the energy. Here is the summary of all the results that we found. We can answer Heisenberg's second question. Yes, given that the energy levels are equally spaced, the Bohr-Einstein relation is satisfied. This is the final answer from Heisenberg's point of view. It is not the position of the oscillator or its speed, but the observable quantities, transition amplitudes, and frequencies. Additionally, we find that the energy of the ground state is not zero, but 1/2 h bar omega naught, exactly as many experiments indicated. In case you're unfamiliar with this, make sure to check my video about the zero-point energy. In that video, I mentioned that there was no room for this factor 1/2 h bar omega in quantum theory before Heisenberg. Bringing back the results of the semi-classical theory of the harmonic oscillator, we see that Heisenberg's theory agrees with all the results of the Bohr-Sommerfeld theory, except for the zero-point energy. In the old theory, the energy of the ground state n equals 0 is exactly 0, in contradiction with many experiments at low temperatures that show that quantum systems exhibit a remnant energy of 1/2 h bar omega. The hope was that a systematic theory of quantum mechanics could explain the origin of this residual energy, and Heisenberg's quantum mechanics did exactly that. If you track the origin of the constant term in the energy, you will find it to arise from the new quantum condition. Born and Jordan transformed this new rule created by Heisenberg into one of the fundamental building blocks of quantum mechanics found today in textbooks, the so-called canonical quantum commutation relation, from which the famous Heisenberg's uncertainty principle can be derived. But this happens 2 years later. For now, I wanted to show you that Heisenberg's paper already contains many of the blueprints for modern quantum mechanics, and although he didn't know it, this formula is the first draft of his famous uncertainty principle. If you made it this far, congratulations, and thank you for joining me. This is a remarkable paper, and I hope that with this deep dive, any student, even at the undergraduate level, can understand its significance and reproduce the original calculations. Most textbooks present these results as coming out of a magic hat, but in reality, they can be derived using some math, a good understanding of the historical context, and more importantly, building out of experimental evidence.